Okay, so this is April 7th, Wednesday lecture. So I'm going to go through some problems that will be similar to the quiz. So we have basically 20, this 14, chapter 14. So 2020, 2019, 2017, 2016 are all pretty much the same. Like they're similar. So all of them have you have some drug in water, and you want to predict liquid-liquid phase separation at 25C. What's the composition of the two phases? And then once you get the composition of the two phases, sort out how much material you've got in the drug-rich phase. Then calculate the crystallization temperature for that and see if it's going to crystallize out a solution. So the crystallization part I didn't go through yet in the class, so I wanted to go through that first briefly. It's just a one equation basically, and then go through this quiz, and then maybe one of the other ones. I just go back in time with the quizzes. So crystallization has to do with solid liquid equilibria. So if you look at the Gibbs free energy, so from the you say like so the Gibbs free energy is H, so delta G for delta G for melting, or delta G for mixing, say, is going to be delta H minus T delta S. And then you can also say dG equals minus S dt plus, so S dt plus P dV. Right? And if you're working at plus V dP, sorry. If you're working at constant pressure, which usually you're in the atmosphere, so your atmospheric pressure, then dG dt at constant P is minus S, right? So the entropy change for a liquid is faster than for a solid because it's more mobile, right? Or the slope of this, the liquid has more entropy than the solid because it's more mobile, like the atoms are moving around more, so they're more random. And the solid's more organized if it's a crystal. So while the solid has a higher, so as you cool down, you form a solid because it's going to have a lower free energy because the liquid has a steeper slope. So at high temperatures, the liquid has a lower free energy, and at some point it crosses over, and the solid, which has a weaker slope, becomes a stable. And that point where those two transition is a melting point for the crystal, where you crystallize out a solution. Generally, your process, you're going to have an organic in a liquid phase in a solution, and you want to precipitate it out, right? So you're looking for this temperature. What's the temperature in a mixture of a crystallizing component and a solvent that it's in? That's like generally the problem here. So how do you take this? Like if you have, say you have a crystal of something, right? Say it's sugar. You're going to put it into your coffee, right? So the sugar is solid, and the melting point for the sugar is something like 150 C, right? So you're not anywhere near the melting point of sugar when you're sitting there at like 50 C, or say you have hot coffee. So you're not getting near T melting. And then there's also a delta H of melting or fusion, right? So anyway, so to get it into solution, you have to go from 25 degrees C up to whatever the melting point of sugar is, 150, then add the enthalpy of fusion to melt it into a liquid, and then bring it back down to 50 degrees C and do your mixing, like X gamma, ln X gamma mixing to the thing. right, to get the free energy change for mixing. So you have a positive change that you have to do to put it into the liquid state. Then you have these two heat capacities changes. And then you have a negative drop in the free energy due to the mixing. So you're hoping that the drop in the free energy is bigger due to the mixing is bigger than the heat capacity changes. So you have to drive it, and the melting, you have to drive it. Right, so you're basically going to end up with this ln x gamma equals some combination of these entropy terms for that process, right? So that's this thing. So you have take it from solid to solid at melting temperature, melt it, delta G fusion, then bring it back down to the liquid state in your coffee, and then do the mixing, which is this ln x2 gamma 2 times RT gives you the mixing entropy. Right, so basically you want this thing, which is dropping the free energy, to overcome all this stuff that you have to do to get it to go into a hypothetical liquid at the temperature of your solution. That's going to be an equation like this. So going from your solid state to a hypothetical liquid is going to involve like this kind of heat capacity change in the heat of melting, and that has to equal this business of melting, and then also this mixing thing, right? So anyway, if this thing is going to be zero, then at equilibrium, at the equilibrium melting point, this delta G is going to be zero. That's equilibrium. That means these two terms have to be equal to each other. So basically you end up with this, that the heat of fusion, or the free energy of fusion has to equal this long term, and the free energy of fusion is going to be this guy, because you have the enthalpy of fusion, right? And we know that the delta S, so if the change in free energy is zero, then delta S is delta H by T, right? So we know delta S of fusion equals delta H of fusion by T melting at the, an infinite size, an infinite pure crystal. So TM infinity, we call it sometimes. Right. So basically this delta S in this equation can be replaced by that. Then you're going to have delta H of fusion times 1 minus 1 over T infinity fusion. Right, for this delta H here. And then so basically you can substitute this, and you can get the melting point T here for this guy, because the T is floating around here somewhere. There's a T here, right? GGDT. So the T is going to show up, and then you're going to have the actual melting point at the condition where you are, and then the infinite, the pure sugar melting point. So wherever sugar melts, the heat of fusion where sugar melts, then the temperature where it's going to melt if it's in solution, right? And that has to equal, that guy has to equal ln x2 gamma 2. Right, so we have this balance between what it's going to cost to get it to that condition, to get it to be dissolved, and then what the mixing, get it to be in a liquid state so it can mix, and then the mixing energy that it gets, those have to balance out. So you get, that's the equation. So what can you get from this? Say you have some solution x2 concentration of sugar, then you can get the gamma 2 from UNIFAC, knowing the composition, the components of sugar, the heat of fusion of sugar at the melting point, the melting point. Then for whatever concentration, I can tell you what temperature it would precipitate out of the coffee, right? Or say you're making a product, so you have a drug, and your drug is manufactured a certain composition of water. From UNIFAC, I can get gamma 2 under those conditions. And then I can know the melting point of the pure drug and the heat of fusion of the pure drug. I measure calorimetrically. Then I can tell you what the melting temperature would be under those conditions, and if your process condition can make a crystal. Right? You have to be below that melting temperature to make a crystal. So that's the melting temperature in solution. Or I think in 2016 it was like to look at de-icing. So this would be the temperature that ice would melt if you put ethylene glycol into an airplane, right? So depending on the concentration. So this is like a pretty useful equation. You can use this for calculating process conditions, right? For instance, if you wanted to plot out as a function of composition, at what composition would naphthalene crystallize out of N-hexane for whatever reason, right? This is a miscible mixture, but they both crystallize. So if you're in the naphthalene poor part of this, what composition will it crystallize at temperature 298, right? So basically you can just change the composition and then see the temperature drops, right? So how far does that drop? Because also, so naphthalene crystallizes, but hexane also crystallizes, right? And this is using this SSCED model that we used before, which is like the Margulis acid base. It's got the AB terms, and it also has the del from the Hildebrand Satchard model. It's like a combination everything model with a kind of a one parameter Margulis. That's what it ends up with. So anyway, so you see that for the naphthalene end. What about the hexane end? So if you look at the hexane end, this is a different system. Basically, the naphthalene end would be here. If you did it the other way around, you'd find out, well, it also there's a melting point depression by putting naphthalene and hexane too, and when it's mostly naphthalene. In this case, it's orthochloronitrobenzene and perichloronitrobenzene. So two things that are pretty close and miscible, but they crystallize into two different crystals, right? So then you get this point where the two meet, and that's called a eutectic point. So you have two crystal forms, alpha and beta, and they meet at this eutectic point. And the way that ends up looking is, let's see, like this. Okay, you have pure beta, which is the para form, and pure alpha, which is the ortho form. And then you have alpha plus beta, the crystals are mixed. These are the melting temperatures dropping. Here you have liquid and beta. Here you have liquid plus alpha, and the compositions of the tie lines across that. Then you have a minimum melting point, which is called a eutectic point. So that's kind of further than I wanted to go. But basically, let me just show you one more thing, as long as we got there. Back here, back here. Okay, so this is that's a eutectic phase diagram. So you have two crystals, mixed crystals. There's a minimum melting point right in the middle. There's an analogy to that with liquid. So you can have two liquids, two liquid states. So we looked at liquid, like liquid alpha, liquid beta. Then in between you have mixed alpha beta, right? So you have this. That also has a varying boiling point. So the boiling point for the dew point drops down until it reaches a minima. So it looks just like a eutectic, except it's liquid. This thing's called a heteroazeotrope. Right, so this isn't really looked at much. You don't usually do vapor-liquid equilibrium, you do liquid-liquid. This one is like super common, eutectic. You can also have something like an azeotrope for crystals, right? This is called a congruent melting solid solution. So this is not looked at much, but the azeotrope's seen a lot. It's kind of like all these things, liquid, vapor, appear in solid liquid, right? But they're just, the most common is a eutectic, and the most common is an azeotrope for the different systems for some reason. There's probably a reason, but I'm not really thinking of it right now. Anyway, so that's all you need for the quiz, right? Just that equation for the crystallization temperature. That's like part D and E of all these. There's like 4 quizzes that are the same. So I can go through this quiz. All right, so this is a drug, ephedrine, decongestant stimulant, and it's got some chemical formula. And then with the Unifac, so Unifac, we can break it down into these numbers. Okay, so it's unifac. I'm taking out the amine groups here. I have a hydroxyl. I have an aromatic hydrogens. There's 5 of them. 1, 2, 3, 4, 5. There's a methyl group. There's two methyl groups, one there and one there. There's a methylene. There's 2 of those somewhere in the middle. Right. So basically, I said like this represents that thing according to group contribution. Yeah, there's definitely something missing that doesn't put it together, but basically this should have something to do with how it chemically interacts with things, right? So we can put that into see, I'm not sure I opened this. This should be quiz 12. Forgot to open this thing. Quiz 12, 2020. Better off. It's going to do it. So we're going to use this unifac to get the gammas for this guy. Quizzes 2020. I think this is online, this Excel sheet. Quiz 12. Quiz 12. Activity coefficient 2020. That kind of looks like it. Okay, so this is first off, you want to know. I'm going to go over here while it opens. So you're going to have it's extracted from green plants using ethanol. So you soak the plants in ethanol. You may have done this, or you can use sometimes oil or something to extract at elevated temperature, and then you do a solvent exchange with water. So you kind of mix water with the ethanol, and then you get separation of this ephedrine to the water phase. So when a liquid-liquid phase separation occurs. So water and ethanol, I guess it's saying they separate at 25 degrees C. Liquid-liquid phase separation. So you're gonna have water, ethanol in both phases, but one of the phases is going to be rich in ephedrine and the other one's going to be poor in ephedrine. Right, so you're concentrating the ephedrine in the ephedrine-rich phase. So you have to determine which phase has the ephedrine in it. So it's saying what's the composition of the 2 liquid phases. That will form at 25 degrees C. First, assume that alpha is pure 2 and beta is pure 1. So we're talking about the water. So you separate the ethanol. The water separates the ephedrine from the ethanol, and you have water. So you're just going to have water and ephedrine, and it's going to make 2 phases. That's the idea. So you have alpha is pure 2, so 2 is water, and 1 is ephedrine, EPHE. Right. So you want to find out what are the composition of the 2 phases that you have, and then use this unifac LLEA to get the gammas, which hopefully is opened here. All right, so LLEA. So here, these are the numbers. Ephedrine is 1, so it's got, and these are all, everything's set to 0. Otherwise, in waters, that's a composition, right? To get the 2 gammas, right? So this is going to be iterative. We're going to change the so the temperature is set to 25 C. You have to do that, and the pressure doesn't matter here because this is liquid, so it doesn't make any difference what the pressure is. And then these are some numbers that it's using to calculate, and then we have the PSAT is calculated from the temperature, and then we're putting in the X values here, whatever those are, X. So those are the things we're changing. Right, and then we put in these numbers to say what chemical composition. So it's water is just 1 water, and the other is these numbers that were given somewhere in here, 22511. Right, so it's like 2251. another one down at the bottom, 1 for the aromatic amine, right? So we just have to put in composition to get the gammas from this. So something like the Margulis model, where we have like gamma equals A12 x, so gamma 1 is x2 squared. So this is like that, like the input here is x. And then from that we get gamma. So x2 gives you gamma 1, x1 gives you gamma 2. That's more or less what way this thing works, right? I mean, there's also an asymmetric part to it where it also involves x1 for gamma 1, but basically it's like the Margulis thing, like that. So we change the x, we get the gamma. That's the idea of this. Then that's what we're going to use the spreadsheet for, right? So that's said. Then we want to know the composition of the phase. So initially you assume pure that phase A is pure 2, so alpha is pure water, and then beta is EPH, whatever it is, EPH something. But so, and then iterate until it converges, use that thing to get the gammas. So let's see. So these are the numbers. So basically, first you say that because you say that these are pure, alpha is pure water, then x, and water is 2, right? And beta is pure epinephrine, which is 1. So that means the epinephrine, the 1 in phase in the alpha, is going to be 1 over the gamma 1 for this epinephrine. So we can put in that, we can get that gamma 1 infinity. So that's 639.2, right? You get that from the sheet by going by saying that let's see, this is x alpha, right? And alpha is pure water, so 1 is 0 in that. So we say 1, 0. We say this guy is 1 e to the minus 20. Like I said before, you have to put in like a number there. It can't be really 0, right? And then this guy's 1. And then you should get 6392 for that. 6392 is the same number, so you can get the x1 from that. So x1 is going to be a really small number, right? And then similarly, you can get, like if you put this one as 1 e minus 20, and then make this one 1, then you get the other gamma for the pure components for the initial, 1.257. So x2 beta is 1 over gamma 2 infinity equals 1 over 1.257. So those are your initial x's for liquid, right? 1.2, right? So anyway, so those are the 2 initial x's, and from those initial x's, so you put those in here. 0.15 and 1 minus that gives you x2, and then x1 is this 0.2045, and then 1 minus that gives you x2 beta. And then you can put those compositions in. You can put those, like for alpha phase and for beta phase, you can put those compositions in and get new gammas, right? So if you put in, so these are so close to pure that it doesn't shift it much. So 639.2 is up 622.61, and the other one was 127, ends up being 4. So then you get, that's for the alpha and the beta phases, like when you put in these numbers. Those are all given in this. So I have so I'm gonna put in like x1 alpha, x2 alpha, so it's 0.000156. So that 1 would be 0.0056, and 2 is 2 is 0.9998. Right, and then that gives me 6260, which is that number that I had here, 6261. Right, so now you put in the beta to get the beta one. Just type in the composition, gives you the gammas. Then I have the gammas, and then once I have the gammas, I can use the gammas to get the K ratio, right? So the gamma ratio, if it's 1 alpha over 1 beta, x1 alpha over x1 beta becomes gamma 1 beta over gamma 1 alpha. The same for K2. And then those are the two K ratios. I plug those into this to get the new X's. And then once I have the new X's, I plug those back into UNIFAC, get the new gammas. So these are the new gammas. I use those gammas to get the Ks. Once you start doing this, it becomes like routine, right? Setting up the first one is difficult, but once you get going, then you just do that until it converges. I think it tells you to do it so many times. Then finally you get the composition, which is pretty dilute, right? And the other one's rich. So, so you're looking at one is the thing you're trying to get. So you're getting, so you end up getting, number one is almost none of the one, the alpha phase, which is a water phase. And then, or 2 is the water phase, and 1 is the, let's see, beta, alpha is the water phase, right? So that's almost pure water. But the epinephrine phase has a lot of water in it too. So X1 beta is only 46%, right? So you're not getting a huge concentration of the stuff. So, but all of it is in the beta phase, like there's none of the one in the water phase. Right, so your total amount of epinephrine is going to the beta phase. That's good. So you have this composition 46C4.536 at 25C between the two phases. Right, so that's good. That's part A. And part B, so sketch temperature versus X1 and show the two-phase region with your two equilibrium points as well as a curve demarcating 1 and 2 phase. So this is just show me what's going on here. Like this is just to say, show me what's going on. So we just calculated the alpha, this is X1, your drug, right? And then it's really dilute in the alpha phase, it's almost pure water. And the beta phase, like 50%, right? And then this line would be like if we calculated at different temperatures, right? That's kind of what we expect, some shape like that. If we did a higher temperature, we'd get lower concentration drug in the water phase. We went to higher concentration, we get higher concentration. Basically, it's a fairly steep decline, so we're not going to see much enhancement by cooling it down. So it's probably just as well to run it at 25. We could check it. We could check 10 degrees and see if cooling it helped. Basically, we're at 50%. So then the question is, if we crystallize it, we'll get pure drug powder, right? That'll settle out, that we can separate by decanting. So we want to take that and crystallize it. So the question is, what is the temperature of crystallization for this guy, right? And it says, I think in the problem statement, that the pure drug crystallizes at, it says here, the binary is fed from liquid, or the first it asks like, how much are you getting? Like how much of the drug are you getting? But here it does give the melting point of the drug and the enthalpy of fusion and the molecular weight, right? So that's what you need to get that crystallization curve. That crystallization curve, yeah, you add afterwards, right? So anyway, so C, binary, this is important, see. So you want to know, so you're feeding into this thing some composition, right? In other words, you start with a water solution that's 25% drug. And you're separating it into an alpha phase that's pure water and a beta phase that's 50%, right? So question is like how much volume is the alpha phase and how much volume is the beta phase? And you get that from the tie line. The tie line is kind of like a, it's going to be like the, so when we did flash before, we had a feed and we had a vapor and a liquid that came out. So we had V by F, right? Here we have a feed, which is like 25%, right? And then we're going to have these two things that come out, beta and alpha. So instead of vapor and liquid, we have beta and alpha. We want to know like what's beta over feed, like what's our cut? How does it cut to the product? Do we get half of it on the product, 1/100th or what? Like if we get 1/100th, then it's not worth doing. If we get 90%, it's definitely worth doing. If it's 50%, it might be worth doing, right? So how much gets cut over here? So the cut here is governed by the tie line. So you have the distance between these two. This guy was like 0.5, this guy was 0. So it's going to be basically 0.5 is the distance across. And this guy's coming in at 25. So we can say that the split of this is 25 over 0.5 is about 1/2. Like 50% goes to beta, 50% goes to alpha, roughly. It's a little bit less than that, right? And then if we know the composition of beta, so if say you fed 1 mole, then you're going to get out 0.5 mole. And if your fraction coming out is 47%, then you're going to get like 0.25 moles of the drug in the product, right? And then 0.25 moles of the drug. Well, your feed was 25%. So that's all the drug that you had, right? 0.25 moles and 25% molar. This means you took all the drug into beta. So at least beta has all the drug in it. That's what you decided from that. So that's what part C is, to do that, to figure out where things are going. So 0.25 minus 0.118 gives you the left side, right? The left side will give you the right composition, then divided by the total, which is, this one was 0.464 minus the one. So that's the total minus the left gives you the right. So that gives you 53.539, 53.9% goes to the beta phase, and the beta phase composition is 0.464, right? So in the alpha phase is this, so the 0.464 times the 0.539 gives you some like the 25% that you put in, all of it goes into the beta phase. So you multiply the composition, this is the amount, like the moles. If you start with 1 mole, it's 0.539 moles in beta, multiply by X of beta, then you get the number of moles, which is the same as your input. So all the input goes into beta. So that's good. That's a good scenario. That means you're putting all your stuff into the phase you're going to crystallize from. That means you have some potential to get everything out of this. Alpha is what you throw away, right? So this separation is working well for you, liquid-liquid. Then you want to know about this crystallization curve. Like, how do you calculate that crystallization curve? Because you want the thing to crystallize out. You want that curve above the temperature where you are, like above 25. That way it's going to crystallize. If your crystallization temperature is below 25, like if it's water, if it's 0, it doesn't crystallize at 25, right? So in fact, you can put ice on this since one of the components is water. So you want to kind of have a water melting. So as you dilute the water with the drug, the water melting point drops. So you have a depression in the melting point as you put in something into it. Like you put salt in the ice, the melting point drops. Same with putting a drug into ice. So the melting point depression, right? And the same, this drug's melting point is going to depress from 40 degrees C to some number. When you get to the composition, whatever this is, 45, 46%, then it's going to have a lower than the 40 degrees C melting point it has. So what is that temperature? Is it above or below 25? That's the big question, right? So to get that, you're going to use this equation, right? So if you look at this equation, we have the composition, that's good. And then we can get gamma at that temperature, right? So what's the temperature? We don't know the temperature. So we need to get the temperature to get the gamma. We need gamma to get the temperature. So this is an iteration. Guess the temperature, get the gamma, use the gamma, get the temperature. Do that back and forth until it doesn't change anymore, right? So because you have a unifac, you can calculate gamma. So the unifac is the other equation. There's two unknowns, one equation. Unifac is the other equation, because unifac will give you the gamma, right? So basically, basically you're going to calculate, going to do this with an iteration, same kind of thing. What's the crystallization? HF equals 25 TM, blah, blah, blah. This requires iteration of temperature becoming 25C. So remember when you did UNIFAC, it's got temperature here, like 25C, right? So every time you guess first, it's 25C. That's the melting point. Or you could guess 40C. That was the initial. And then you're gonna go back and get the gammas. Then you're gonna go back and get the gamma, and then you're gonna use this guy with gamma to get the T again. So once you know gamma, you know X, you know all the other numbers here, then you can get T, and then you're going to iterate back and forth to get that. So that's the game to play here. Let's see, that's D, right? So blah, 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 T, calculate, use X, get T, use gamma at 25 initially equals this. So you guess initially it's 25, and then gamma at 25 is 0.194, use 0.194 to get T. To do that, you get 310K, plug in 310K into the, which is 37C in UNIFAC, you get the gamma, and then come to find out when you put, or 37C, put 37C in, you get 31C. If you do that again, you get 31C again. So basically, once it repeats temperature, you've found your solution more or less. So you've changed by 1 degree. So the answer is 31 degrees C. So then you can go back to your plot and put in your 31C, which is kind of here. I mean, just hand drew this, but this is above anyway. So your separation is 25, you're at 31, so you're like 6, or what are you? 25, 6 degrees above, right? So you're close. So it's not, you'd want to have a deeper quench than that to really make it crystallize out, because this stuff is going to be syrupy, right? In other words, it's going to be like an oil. So it's not going to be so viscous, so flowing that it can crystallize like so fast, right? And the temperature is only 25. So 6 degrees isn't a huge gap to have this. And if the viscosity gets too high, it won't crystallize. And then you have oil, right? And oil is kind of useless here, right? You just have an oil. So if you concentrate this thing too much, the viscosity will go too high, and then it won't crystallize anymore. And then you're stuck. You just have goo. You can't sell that drug. I mean, some drug you can sell as goo, but basically this one you want to crystallize. So anyway, the question of the feasibility, it's possibly feasible to do this, but it's going to take time. The other thing is, like, how much time do you have to do this? That depends on how valuable the drug is, right? So that's the picture of this quiz. It's basically going to be that. All the quizzes are the same like that, right? So that was the 2021, 2019 is that's the wrong place. All right. 2019 for 12, chapter 14 is different drug, right? This is a drug used for epilepsy, bipolar disorder, schizophrenia. And the problem with this drug is that it can crystallize into different forms. So a lot of these things can crystallize not just one crystal form, there can be many crystal forms. They're called polymorphs, right? And if you get the wrong polymorph, it's useless. So only one of the crystal forms is useful as a drug and the others aren't, right? And all the polymorphs have different crystallization temperatures and enthalpies of fusion, right? So basically each one is going to have a different melting point. So if the melting point of the bad one happens to be much higher than the melting point of the good one, in the temperature we were operating, like 25, then basically the bad one will crystallize faster because the speed of crystallization is going to be the change, the quench depth, like how far are you away below the crystallization temperature, right? So basically you have to be kind of careful about how this operation works if you want to make something that's useful. The other thing is these crystals can seed. So if you happen to make the wrong polymorph, you have to kind of throw away the entire chemical plant, because once there's a polymorph seed crystal available, the only thing you'll make is the bad one. So if you make it once, you're dead. So you have to be really careful what you're doing with this stuff. So that these plants that are making these drugs will have ultra clean, and they'll have a lot of restrictions about people walking around sticking their hands in things. Because if they happen to get one of the wrong polymorphs in some way, then their whole operation has just become garbage, right? You can't use the equipment anymore because you can't wash out the polymorph. It's stuck there somewhere in a crevice. All right, so this is CBZ is 1 and water's 2. So it's the same setup as the last problem. In fact, all these are kind of the same setup. There's 4 of them, 4 or 5 of them here. I think it's a good problem to do because it includes liquid-liquid phase separation and liquid-solid. It doesn't have liquid-liquid vapor. And the other one would be liquid-liquid vapor solid, right? So you could do all 4, but basically these are pretty good because it's also a real industrial problem in the pharmacy industry. And the same kind of thing can come up, like if you're doing battery recycling and you need to crystallize out sulfuric sulfate, like zinc sulfate or something from a solution, same kind of problem. It's just like you're trying to find the crystallization temperature, liquid-liquid phase separation because you did an extraction to get the zinc oxide into some sulfate form or something or other. And then you want to crystallize out the product. So there's many cases, like if you make citric acid, you take molasses, ferment it, then you end up with a slurry in water, then you do a liquid-liquid phase separation and do a crystallization. So this kind of scheme is like a lot in the kind of food industry and pharmaceuticals, right? So anyway, so this is gonna also, and UNIFAC is like my favorite thing here because it's a group contribution. It's pretty easy to use and it comes out. You saw in that paper from last week that it works really well, right? So might as well just use that. There's a bunch of other programs, a bunch of other models that you can use. Depends on what kind of specifically you're looking at, but UNIFAC is a pretty good one. And it's also incorporated in Aspen and in ChemCAD. So in fact, all those programs from that chapter are in those. So if you're doing plant design and you want to know which one to use, you can go back to the book and figure out which one you like better. It kind of describes them. You saw like Wikipedia also describes these models for getting the activity coefficient. Anyway, so let's see. So this is 1 and 2. It's the same thing. Do the first initial assessment of activity coefficients, then 2 iterations. So saying like don't do so many iterations, just do 2. Calculation of 2 sets of chemical and the resulting compositions using, in fact, LLE and it has LEA, LEB because you can have the 2 components calculated at the same time. But basically you can just use LLEA and just keep changing. In other words, you have the alpha and beta phase. So LEA is for the alpha phase, LEB is for the beta phase. So if you have so you only have to type the compositions in once if you use those 2. Basically, you can just keep typing in the compositions and use 1. That way you kind of know what's going on. Let me see if I can find this. This is 2019. I need to wait for this guy again. I think working through the old quizzes, you can get a feel for how this works. This isn't even like responding at all. Did that kind of. It's because this, I think I've narrowed it down that it's this QuickTime is like eating up a lot of. So the thing I'm displaying with the video is eating up a lot of memory or something, or CPU time. Let's open up. I should have opened these earlier, but I forgot to. So we're looking at 2019. It's going slow too. Their quizzes 2019. quiz, quiz 12, right? Part E, quiz 11. Quiz. What quiz is this? Quiz 13. Quiz 13 parts. Quiz 13 activity coefficients. Right here. It's just LLEA. And then the, let's see, the composition of this. What composition of two liquid phases will form at 25? So initially the phase alpha is pure 2. So it's the same as before. Alpha is pure 2 and beta is pure 1. And it's not, it's like this weird thing, C, B, Z. All right, so, and then use LEA, do initial assessment of activity in 2 iterations, just saying that. So it's the same thing, like you do the pure ones first. So it's the same, like I'd set this to pure first, and then, so it'd be like even 1 e to the minus 20, and then 1, and then 1 e to the minus 20, and 1 would give me the 2 pure limiting numbers, and then so these are the 2 pure ones. This one's even worse than the other one. It's 72,000. So the bigger this number is for gamma, the more phase separated it is. That's a huge number. Means, see, you can see e to the minus 5 ends up the composition of one phase. So the beta phase, which is CBZ, is almost pure X1 beta. The beta phase, see, alpha should be water. And X2 alpha. So the alpha phase has almost pure CBZ, is 58% CBZ, and the beta phase is almost pure water. So somehow the numbers got switched here. The 1 and 2 are wrong, because 1 and 2 are right, but beta, water is in beta here. And it's supposed to be, water is supposed to be in alpha. So that in this answer sheet, alpha and beta have been swapped somehow. I don't know why, but that's kind of how it worked out. It started with this point. That's really beta, and this is really alpha. Right. So after that, it just followed through. I mean, I'm remembering this now, but anyway, so once you have the two x's from the gammas, then you're going to use those to calculate. Once you have the x's from the gammas, use those to calculate the x's. You put those x's back into UNIFAC and get the new gammas. Right. So x1 is 1 minus x2, x2 is 1 minus x1. Then you plug those numbers back in and get the new gammas. Then once you have the new gammas, you plug those into that K ratio equation to get the this isn't really spelled out how to do this. But once you have the x's, you plug them into the UNIFAC to get the gammas, and the gammas give you the K ratio, and the K ratio gives you the x's. And the x's, oh, here's the K ratio down here, and the K ratios give you the x's, and the x's give you the gammas. Right? And you just iterate that. So you start assume 0, 1, you get the x's, the 4 x's. So there's 2 for each phase, alpha, beta. Then you use the x's to get a K. And the K gives you a new, use the x's to get a new gamma. And the gamma gives you a new K. The K is gamma 2 over gamma 1, or gamma beta over gamma alpha. Right? K1 is beta over alpha, K2 is beta over alpha. And then the K's you plug into this equation to get the x's. Then the x's go into UNIFAC to give you the gammas, and the gammas give you the K's, and the K's give you the x's. And you keep doing that, right, until it doesn't change anymore. And it turns out it does, the 2 iterations enough, then you get the composition. So it's almost pure water. The 2 is water in the beta phase, and it's 66% drug in the one phase. Right, so that's a pretty good split. It's better than the next quiz. Right, so you can draw that out. You can put in your compositions, and then you can say, like, here's your phase, right? And then you can say, well, that's B is draw the plot, whatever that is. It's here. So B is probably draw the plot. Same thing. Let's say evaporation leads to an aqueous solution. So you have 30% as your feed. So your F is 30%. So what's a fraction that goes to the alpha and beta phases? So what, use the tie line to get the composition. The same thing. So you're coming in at 30%. Then so this one to the left will give you the right. Right. So you want to know 30% minus almost zero. That's the gap, and the total gap is 0.66. It's going to be 30 over 0.66 is something like 50. So 45%. So it's 45.5% goes to alpha. So alpha by feed is 45%. The number of moles, if it was 1 mole that came in, you ended up with 0.455 total moles in alpha, and the total moles of drug in that is 0.4455 times whatever, 0.66, which should end up equaling 30. Because it's almost all of it's going to go in that phase. So take, see if that works. So we take 0.455 times 0.66 gives you 30 exactly. Right, so it all goes into that phase. So that's good. So everything kind of balances out. So in that case, you know how much of this you're producing and where the stuff goes that you put in. It all goes to that phase. So you're at that phase at 25 degrees. It's got this composition up here, 0.34, 0.66 drug, 0.34 water, and you want to know where does it crystallize then, right? So what composition is it? What composition does it crystallize? So let's see what part C is here. Part B, let's see. What would happen if you evaporated to a much higher concentration? So if you came in with a higher concentration, you'd have just a syrup. It wouldn't separate at all. You wouldn't separate into two phases. It would be syrup, and you couldn't enrich that because outside it would be in the single phase region. Right, you know the composition 0.66 is what's at equilibrium at 25. If you came in at 0.8, there'd be no separation. It's a single phase, and it would be syrupy. So you couldn't make a crystal from that. Right, so you want to be like in this range between 0 and 66% for your feed. So you could concentrate it up to 0.6, and then you would get a separation to a little bit stronger, and then you could crystallize if you wanted. But the situation is, then D is the same routine. So you got this equation for the temperature. Gamma is going to depend on X. So you guess X at first, or you guess the temperature at first and get gamma. So gamma depends on X and temperature, right? So X is fixed. You got the composition fixed at this composition, 0.660. Right, so you get 0.660, and then the temperature you don't know. If you're trying to find the temperature of crystallization, you know the crystallization temperature for the pure crystal. You know the heat of melting. So you can get the temperature if you know gamma, but gamma relies on knowing the temperature. So you have to guess the temperature. You say it's 25, then get the gamma, then get the temperature. So you get the temperature. It's for 29K 156. It's much higher. Right, and then you reiterate. You take 156, put it in, get gamma from UNIFAC, and then you get the composite. Then you get the gamma. Once you put 156, you get the gamma. Then with the gamma, you can get the T. It comes out 151. Right, and if you do it a couple more times, you end up with 152. See, so the crystallization temperature is 152. So if you go back to the plot, you're at 25 and the crystallization is 152. The minute this thing goes over there, it's going to crystallize out. So it just comes straight out of solution. right? So the minute that it gets there, it comes out. So that's a good scenario. It's really fast. Boom, it's going to make a crystal. So that's kind of what E is. It will crystallize fast because it's a really high crystallization temperature. So the others are similar, you know, it's kind of similar, basically exactly the same. Like 13, if you go to it, is the same thing. It's paracetamol, so like Tylenol, and then it's crystallizing, same 25, same thing. Use Unifec. It's the same problem. So you probably see the same problem with some other drug. That's the idea. So work through these, see if you can do them, and then probably will be the same thing. I like this problem, so I think it's a good. It's kind of good, you know, to see. The older quiz is something about ethylene glycol for freezing, you know, prevent freezing for airplanes, and then something ethyl acetate, equimolar mixture. Some, you know, it's a little bit more, I don't know, choppy. I like the drug thing, so probably give you another drug problem. And then I guess I'll see you on, if you have questions, email me. You know, hopefully you can work this out. And then I'll see you on like a week from Monday, I guess, probably. But I can be answering the emails, so I can help you with the things with that. So good luck. I'll see you.